For this lesson, we're going to be extending what we did in the previous lesson and looking at the vector and parametric equations of a plane. In the previous lesson, we talked about the equations of a line. In particular, we looked at three different forms of an equation of a line in R3. One of them is the vector equation of the line, and the vector equation of a line is made up of a initial position vector, and then you add to that some sort of direction vector. We can then break out the individual components. The x component, which is made up of x naught and t times a, ends up being this parametric equation, and then the y coordinate and the z coordinate. And then finally we talked about how you could form what's known as the symmetric equation. And the way you would do that is you would isolate each of these parametric equations for t, and you would set them all equal to each other. Now for today's lesson, we're going to be focusing on the vector and parametric equations. So first of all, let's talk about a vector equation. Now the first thing, let's make clear, we are not talking about a line anymore, we are talking about a plane. And we've had a number of conversations where we've informally discussed the idea of a plane. And if you can recall those conversations, one of the ways that we described a plane is essentially we said if you have two vectors, so long as those two vectors are non-collinear and non-zero, they describe a plane. And so that is what I'm doing here with these two direction vectors, d1 and d2. And since they're direction vectors, I can also multiply each of them by some scalar value. And I really should say here that m is a member of the reals and n is a member of the reals. Now with this you might notice, oh, the letter m, we were just using the letter m as a direction vector. We use letter m for slope. This is just the reality of mathematics. We have to reuse symbols, we have to reuse letters of the alphabet, and you just need to be robust enough in your understanding of these things that you don't allow it to derail you when stuff like this happens. So in this particular representation, I'm using m and n for my scale factors. I'm still using r naught, the vector r naught, to be my initial position vector. And so if I were to represent this in terms of components, one possible representation might look like this. So this is my vector equation of a plane in component form. Now in order to give, this is a very difficult thing to visualize unless you're actually in the 3D world, and even that's difficult enough. So we'll go through an actual physical demonstration of this in class, but I was able to find a GeoGebra demo. I can't take credit for this. Someone put a lot of work into getting this to look as good as it does, and even this is difficult to get your head wrapped around. So I'm starting off with the X, Y, and Z axes, and I've oriented them in a way that is familiar to you, hopefully. This gray shaded area, this actually represents the XY plane. So I can actually move, and you can see if I shift things around, that gray area is staying consistent with the X and Y plane. So that being the case, now let's get into the idea of the vectors. So what I have on here are three different vectors. The first one, the red one, and I'm going to just choose a slightly better position for this. The red vector, that's going to be our initial position vector. So that red vector is r naught. So that is describing some point, and everything is happening from that point. Then I have the blue and the green vectors here, and those represent our two different direction vectors. So those, in this case, those two different direction vectors, a linear combination of those, if I stretch these vectors or if I compress these vectors, they will form, those two vectors together, the blue and the green, they will form a plane. And then the red vector tells you where that plane is in 3 dimensions. So you can kind of see it there. As I go to these different orientations, you can see the surface if you're good at visualizing things, you can see the surface that that blue and green pair of vectors make. For example, that's us looking at the surface from the side, so we're looking at the edge of the plane, and this is us looking at it from above. I can actually turn on the plane, and you might look at that, that might not add much, but if I rotate this, you can see there is that blue plane. Those two, notice that those two vectors, the blue and the green, they lie inside that plane. So those are the two direction vectors. And notice that the red vector, that position vector, actually connects the origin to a point on the plane. But that position vector is not actually in the plane itself. Okay, so that is our idea of what do we mean by a plane being made up of a position vector, which is the red one, and then two direction vectors. Okay, so from that idea, so a plane can be described by a vector that goes to every point is possible on the plane, because we start off with a position vector, which is one point on the plane, and then we span the plane. So this is a spanning set, D1 and D2. We span the plane, and then we just do multiples of those vectors, and that will allow us to explore every single point or every single position on the plane. If I write that in component form, I get this equation, and I can split out a parametric equation or a set of parametric equations from this vector equation. The x component is going to be made up of the initial x component, and then we have our scalar multiple of the first direction vector plus our scalar multiple of the second direction vector. And we end up with these parametric equations. So I've tried to give you a visualization. This is the algebraic part of it. So let's go ahead and manipulate some of the algebra. So find the vector equation of the plane containing these 3 points. So once again, my vector equation is going to be written as the initial position vector plus a linear combination of a couple of position vectors, or not position, sorry, direction vectors. So what are the choices? My initial position vector, in this case, I actually have a few choices. I could choose between, my initial position vector points to one of the points on the plane. It is the position of one of the points on the plane. So the initial position vector could be the vector OL, or it could be the vector OM, or it could be the vector ON, because L, M, and N are all points on the plane, and so the vectors OL, OM, or ON, those point from the origin to the plane. So that's our first choice. And then for my direction vectors, I have choices as well. I need vectors that lie within the plane, so I need two vectors within the plane. So what two vectors might lie within the plane? Well, since the point LM, both of the points L and M lie in the plane, then that means the vector LM lies in the plane. The points M and N lie in the plane, which means the vector MN lies in the plane, and LN lies in the plane. And so I have 3 choices here, and I just have to pick 2 of those choices in order to make up my direction vectors. So for example, I might choose, so for example, this is not the only possibility, but if I make some choices, I'm just going to do them in the order that they're provided. So I'm not going to get I'm not going to get fancy. I'm just going to choose my first choice, which is OL, plus some scale factor times LM plus another scale factor times MN. Now you need to also figure out what these different vectors are. So maybe off to the side you might want to make a note of the fact that the vector LM is equal to OM minus OL. And if we do OM minus OL, that's going to give us the vector M minus L. That's going to give us a negative 8. And 4 minus 2 gives us 2. And 0 minus 5 gives us negative 5. And similarly, if I did Mn, the vector Mn is the vector On minus the vector OM. And so from there, I end up with 3 minus negative 7, which gives me 10. And I end up with 1 minus 4, which gives me negative 3. And negative 2 minus 0, which just stays as negative 2. And so now that I have those, I can say my vector r is equal to the vector OL is just the same as the point L. So that's just 1, 2, 5 plus my first scale factor times LM, which is negative 8 to negative 5, plus my second scale factor N times my second vector, my second direction vector, which is 10, negative 3, negative 2. So there we have one of our possible vector equations for the plane. Now, there are actually many. I could have chosen any one of these as my starting, my initial vector, my initial position vector. So that's 3 options there. And then here, there are 3 different combinations. And the opposite vectors to each of these would have been valid as well. So for example, ML would have been valid. So technically that's 6 vectors. So you can see that there are actually a number of different ways that I could have correctly represented this plane. Okay, exercise 2. Does this point lie on the specified plane? And in this case, I've given you the plane in terms of the parametric equations. So in this case, you can see my scale factors don't have to be M and N. G and H is what I've used as my scale factors in this case. So if this point lies on the plane, then that means, so if we call that the point P, so I'm just going to say, so let the point P 4, 5, negative 3, and if that's the case, then that means the vector OP is also 4, 5, and negative 3. Now if I start from there, then what we're really going to do is we are going to test if this x, y, and z value, if these x, y, and z components of the vector go into the parametric equation. So I'm basically going to be testing, I'm going to test the vector OP in the parametric equations. So the first one becomes 4 is equal to, the x is equal to 4. 4 is equal to 4 plus 3g minus 6h. So that becomes my first equation. My second one is the y coordinate. That is 5 is equal to 1 minus 2g plus 6h. So that's call that equation number 2. And then my third equation is negative 3 is equal to 6 plus g minus h, and call that equation 3. I'm going to do a little bit of simplifying here. 4 minus 4, that actually ends up giving me 0 equals 3g minus 6h. Here I end up with 4, because it's 5 minus 1 equals negative 2g plus 6h. And then here I end up with negative 9 equals g minus h. So now that I've done that, I take a look. I prefer elimination. I notice I've got a negative 6h here and a positive 6h here, so I can actually just go ahead and rewrite this equation. 4 equals negative 2g plus 6h. And if I just add those two equations together, I get 4 on the left side. 3g minus 2g is just equal to g. And then the negative 6h plus 6h cancels and I end up with 0. So I get g is equal to 4. Now that I've got that, now that I have g is equal to 4, I can solve by either putting that into equation number 2 or equation number 3. Now I can solve for h, I meant to say. Now equation number 3 looks like the simpler one to solve for h because I just have a linear term in h. It doesn't really matter here, but I'll save myself complicated arithmetic whenever possible. So that becomes negative 9 is equal to, my g value is 4 minus h. And so I bring the h actually over to the left side, and I bring the negative 9 becomes positive 9 over to the right side. I end up with h is equal to 13. So when I go ahead and do that, one thing I haven't done is I need to make sure that these answers are consistent. So now I need to check, and I'm going to check here. I'm going to go left side. Well, left side is equal to 4. Right side is equal to negative 2 times g, which is 4, plus 6 times h, which is equal to 13. And that is equal to negative 8 plus, and that's 60, 78. And that is equal to positive 70, which is obviously not equal to that left side. So since my left side is not equal to my right side, therefore, and what are we asking here? 4, 5, negative 3. 4, 5, negative 3 does not lie in the plane. Okay? You could have done this another way as well. We could have subbed our value of g into here, and then we would have gotten, let's see, negative 2 times 4 is negative 8, and then we take that to the other side, it's 12, and then we end up with an h value of 2, and then we go and check over here and we get an inconsistency. So in either case, we still would have gotten an inconsistency regardless of which one we verified with. So, example 3. Where does the plane pi intersect with the line L? So, rather than calling the plane P to represent plane in the same way that we use L to represent line, this is a convention that you see quite often in mathematics, which is planes are often represented using the Greek letter pi. And so once again, we are duplicating the use of a symbol, but the contexts are very different, and you need to use that context to help you keep things straight. So here's the definition of the plane. It's made up of an initial position vector and two direction vectors. Here is the equation of the line, and for this one it's actually worth pointing out that since there is no initial position vector, the initial position vector is actually 0, 0, 0, and then the direction vector is 0, 1, 0, which is given. So the question becomes, is there some way that we can reconcile these things? In other words, is there some way I can get this position vector to be the same as this position vector? So we want the position vector for the plane pi to be equal to the position vector for the line L. That's essentially what we're asking if we're looking for an intersection. We're saying, when do these two positions occupy the same point or direct us to the same point. And so what we actually are going to do is we are going to take the vector equation of the plane, which is 6, -2, -3, plus m 1, 3, 0 plus n 2, 2, -1. Just clean up that plus sign. And we want that to be equal to t times 0, 1, 0. And so in doing that, we're going to be able to form a system of equations. And that system of equations is going to be 3 equations, and that's good because I've also got 3 unknowns here. So the x coordinates have to match up. So we end up with 6 plus m plus 2n has to be equal to 0 times t. Well, that's just equal to 0. That's our first equation. And then the y components are going to give us -2 plus 3m plus 2n is equal to 1t, which is just t. And that's equation number 2. And then the z component, -3 plus, actually, -3, and that's going to be plus 0m, and that's just 0, minus 1n is equal to 0t, so that's just equal to 0. So from there, we can actually solve this immediately. This third equation immediately yields that n must be equal to -3. And so now that I know what n is, I can actually simplify my other 2 equations. I end up with 6 plus m plus 2 times -3, because I know what n is. That's equal to 0. And so this is 6 plus m minus 6 is equal to 0. And so obviously then we get m equals 0 because I had 6 minus 6. And now that I know that m is equal to 0, I end up with -2 plus 3 times 0 plus 2 times -3 is equal to t. And then I end up with -2 plus 0 minus 6. -2 plus 0 minus 6 equals t. T is equal to -8. So that's what we end up with as our point of intersection. Now, a potential confusion here, and it would be reasonable to be a bit confused by this, is you might look at this part and say, oh, well, hold on, you're setting that coefficient to 0. Doesn't that mean you're throwing away one of the direction vectors? Maybe it's not a plane anymore. And maybe you can tell by my tone of voice that no, that's not actually the case. When we talk about the plane and we talk about these direction vectors, if I make one of these direction vectors equal to 0, let me see if I can't simplify this a little bit. Let's bring this around here. Oh, I don't want that. If I make one of these direction vectors equal to 0, I'm still on the plane. It's just that now the only vector that's moving me around the plane is, in this case, the green vector. This point is a point on the plane. So it's okay that we ended up with that result that m is equal to 0, because we are trying to find where does the plane intersect with the line L. That's a specific point. So now that I know my values for m, t, and n, now I can actually sub that into, I could put it into my plane equation or my line equation, but my line equation is so much easier. Since my line equation is just r equals t times 0, 1, 0, well, that's equal to -8 times 0, 1, 0, which is 0, -8, 0. And so therefore, my point of intersection is 0, -8, 0. We could have done this the hard way, which is we could have subbed the values for m and n into the plane equation, but we would have gotten the same result. And I'll leave that to you to verify. Okay, so that's it for this equation. Nothing difficult in the algebra we've done here. The most common thing we did here was solving systems of equations, but the concepts are difficult. So make sure you ask if you have questions about this.